So today we have a talk by Tam Vu, who comes from Vietnam and got his undergraduate degree at the University of Hanoi in computer science. Then came to the US to do his PhD at the University of Rutgers. And after that, he basically became a faculty member at the University of Boulder, Colorado at Boulder, where he develops new types of sensing systems and other types of sort of systems for health and well-being. He's specifically interested in sort of smaller, cheaper solutions to some of the sort of problems that we're dealing with and that we currently have faulty solutions for. So I'm very excited that we were able to convince him to come and speak, and I look forward to hearing it.
Thank you, Pat. Thanks for having me. Thanks everyone for coming. Today I'm going to be talking about a common problem that we see almost every day: sleep deprivation. Right. Probably if you look to your right or if you look to your left, you probably find one that is sleepy. So my job today is try to keep you awake, okay? Well, so statistically, there's more than 1/3 American have sleep deprivation, and it's a serious problem. It's a health problem that would affect not only adults but also kids, and it has a wide range of chronic health problems, ranging from depression to hypertension, stroke, diabetes, among many other diseases. And with kids, it causes serious consequence when they have sleep deprivations, right? I hope you don't find this kid at home, right? But so the kid can have excessive sleepiness, or it can cause obesity, allergy, and poor school performance, among many other health problems. And it's so serious that the American Academy of Pediatrics call for early screening of a kid with sleep disorder and with symptom, right? So what is the current practice to do such sleep screening and sleep study? This is what we see. This is a relatively happy kid that's carry, and I'll explain why it looks like happy, right? But what the kids normally have to wear is a bunch of sensors. Normally, it's ranging anywhere from 30 to 35 sensors that are mounted on their head, on their body, and on their limbs. So these sensors basically divided into three key groups of sensors. One are sensors that mount onto their head to monitor brain signal, eye signal, muscle signal. And the other group of sensors are mounted on the chest and the nose to monitor the breathing patterns. And the third group of sensors are mainly mounted onto their body, their limbs, to diagnose the reason for their sleep not being very well. So this is a happy kid, and this is an actual kid this is a picture that I captured in the Colorado Children's Hospital 4 years ago when I first joined the university. And as you can see, those sensors need to be wrapped around. And the reason for it is, if the sensor was left exposed during sleep, kid would take those out. Because unconsciously, when we're sleeping, if there's anything that causes uncomfort, you would just try to take those out, right? For that reason, the sensors need to be wrapped around. And of course, the doctor would ask them to sleep normally. Right? Imagine you go into the hospital, when you move from your comfort bed into in-hospital environment with all that sensors on your body, and then now they ask you to sleep normally. It's pretty hard, let alone that for the kid, right? It is uncomfortable for one, but it also required expert setup, which normally required anywhere from 30 to 45 minutes to set those 30-something sensors up on the body. And not only that, after the sleep study, expert would need to sit down. Normally, those are the sleep doctor or physicians would need to sit down and read the output of these systems. And because of that, it costs anywhere from $2,500 to $5,000 per sleep study. So because of this problem, it is very expensive and uncomfortable and sometimes inaccurate to do this kind of study in hospital, right? And another footage that I captured from our hospital is this kid, where he was sleeping and then he woke up in the middle of the night. And what he was saying is that my face feels like really smothered. And the sensor here, you see that the kid would try to take those sensors out, and the very wires and sensor, they would wake him up because he feels that those sensors are pointing into the kid's face. Because of this problem, what we ask a question, we ask a question of whether we can create a new gold standard, a new polysomnogram that satisfies certain properties. One is that it should be less obtrusive. It should be inexpensive. It should be simple to use, and at the same time, it should be accurate, right? So that is the mission that we set out 4 years ago to try to replace the gold standard polysomnogram device. And what that meant is that we need to replace a lot of sensors, sensor here and the sensor for breathing, among many other sensors. But for the scope of today's talk, I will be only focusing on a set of a device that we designed to capture the signal from the brain, eyes, and muscle. So the question we ask here is that can we remove those wires and at the same time keep the cost really, really low? So before we try to replace something, we need to understand why it's there in the first place, right? So a little bit background about sleep study and sleep monitoring. So humans sleep normally divided into 5 different stages. Start from awake, of course. And during that stage, if we look into your brain signal, your brain wave normally range from the frequency is range from 8 to 13 hertz. And as you start drifting into sleep stage, which is sleep stage number 1, your brain wave starts slowing down. And as you go deeper, it's a little bit counterintuitive here that your brain signal is actually speed up a little. And there's some patterns of the signal, for example, some spindle signal and also K-complex signal, which means the shape of those brain signal have a typical characteristic that when the doctor looks at those signals, they can tell what sleep stage you are at. Now, so far, what we can see is that if I have access to the brain signal, I should be able to tell which sleep stage you are at. Right? By just look at the brain signal. But as you go deeper into sleep stage number 3, we need to have, and sleep stage number 4, which is rapid eye movement, we need to have access to 2 other kinds of information. One is the muscle signal, which is the chin tone, because as you go into sleep stage number 2 and 3, the chin tone is completely relaxed. Your jaw is dropped. And without knowing that, we will not know which sleep stage you are at. And sleep stage number 4, in order for us to know, we need to have access to your eye signal. Because during rapid eye movement, as it's suggested from the name, your eye would move really fast, right? Mm-hmm. So we need to have access to the eye signal in order to tell whether you are in the sleep stage number 4 or not. So that is what the current polysomnogram or the gold standard try to classify your sleep stage into, right? 5 different stages. And so there are existing systems that try to do sleep staging. For example, you can download a few applications on either Apple Store or Android market to try to monitor your sleep quality. And what it does is that you just download the app, one application would call Sleep Like Android, which is a very, very popular app you can download, and you might see that there's probably 50 million downloads out there. Now, what the application does is that it will listen to the sounds that you would make when you're sleeping on the bed. And the sound is mostly caused by the friction of the body movement. So essentially what it does is that it infers your body movement. And from your body movement, it will say, well, you're moving, meaning that you're not sleeping. And when you're moving often, then you're not sleeping deeply. So that kind of inference is a measurement of an estimation of your sleep quality indirectly through body movement, right? And of course, because you don't have access to the key informations, as I mentioned, of 3 main signals, brain, eyes, and muscle, these kind of estimations are not accurate. And the same is applied for wearable devices such as Fitbit or Apple Watch, where they just based on your body movement and in fact, limbs movement for the most part, right? Because of that, it's not very accurate. And the reason that it's not accurate is because, again, it doesn't have access to the 3 key information. Now, there are, addressing those problems, there are devices that was built to capture your brain signal, or the wearable device. And one example here is a device called Zeo. The company has started, I think it's back in 2008, and filed bankruptcy sometime in 2012. The reason is that it's not very accurate and it's very uncomfortable to wear. What we did when we started this project is we tried those devices. We bought 5 of them. And of course, we started this in 2013, and that was the best device out there based on the review. And because the company has gone bankruptcy, we have the only way to get access to those devices is go on eBay and try to buy those, right? We bought it from eBay, we set it out, we have IRB to do an experiment where we have our subject try to do a sleep for 1 week. And we want to see the accuracy. The accuracy of the Zio is around 40 to 50%. There's 2 reasons that contribute to that inaccuracy. One, people would try to take the headband out when they're sleeping for the same reason that I just mentioned. Because it's uncomfortable, you would take it out. That's one reason. Now, the second reason is that the device would fall off during sleep. Now, why does it fall off, right? It falls off because of the friction that you would cause because of the body movement, and as you move, the friction that the device have with the pillow would pull the device out, and because of that, it's the contact between the device and the forehead is no longer there, so it's become not accurate. And another reason is that because it only have access to the brain signal, it can't estimate the sleep stage as well as if you have the other 3 signals, right? So what we were trying to do is we tried to come up with a device that can provide all 3 signals. It should be less obtrusive, comfortable, and at much lower cost, right? So what we introduced is a system we call YES, with the I instead of the Y. And it's a lightweight, inexpensive in-ear bioelectrical sensing system with the idea of measuring those signals from inside human's ear. And the reason that we try to measure this signal from inside the ear is because, first of all, if you have an ear plug inside your ear, the chance of the device to fall out from your ear is lower than having something that you have on the forehead. But the more important reason is that is a relatively good location to, with respect to the signal source signal of interest, right? It's because it goes through your skull already, so it have a closer distance between the earpiece and your eyes, and also it's relatively close to the muscle and also the brain. So that's why we pick this location, and that's why we say, let's give this a try. Now, the goal here is try to capture all 3 signals at the same time, but the first challenge is coming from the fact that because we have very small area inside the ear to do the measurement, we can only have a pair of electrodes inside the ear. And because we only have a pair of electrodes, the signal that we have is only 1 channel. We have one channel of signal, but at the same time, we are interested in 3 different signals, right? Plus noise. So the key challenge here is that we need to be able to split these signals from, we need to be able to split those 3 signals out of the single signal, and at the same time eliminating noise. The challenge is coming from the fact that those signals are overlapping in frequency and amplitude. And not only that, the signal is different from one person to another person. And if you try to measure from the same person at different time of the day, and every time you put the electrode inside your ear, if you don't push it inside deep enough, the contact point will be different, and the signal would also be different. So what it meant is that it's different from people to people, even a person per person, and it's also different. Within the same person, it can be different as well. Right? So what we introduce is a non-negative metric factorization algorithm to split the signal out. The key idea here is that if we can represent the signal that we can get from the inside the ear as a time series that is a linear combination of the 3 signals of interest and the noise, then, and if we can factorize that into two parts. One is a spectral template metric, which essentially show the component of the signal that relatively stable, because different people might have different patterns that are relatively stable, and which is the metric W here, and H is the activation metric where it will show the weight of each component on the relatively stable metric at any given time. So if we can defactorize that, then we will know, okay, we can calculate each component, right? So the high-level idea here is that, okay, if we look at the frequency domain and we can split the signal out, then if we can defactorize the signal, then later we can go through the iteration and we can recompute the 3 original signals. So we formulate this as an optimization algorithm where we would try to represent X in terms of W and H. so that the distance between W, between the product of W and H to X is minimum. Now the key here is that we need to also define what is distance between the two space, right? So we picked a Itakura-Saito divergence measurement as a representation of the distance so that it's invariant with the scale of the signal. Because as I mentioned, if you push the earpiece inside your ear very deeply and push it well, and the contact point is good, then you have a very high amplitude, a good signal. But if you don't push it very deep in, or if it gets pulled out a little bit, then the signal is significantly reduced in amplitude, but the frequency domain should still stay the same, and also the shape of the signal should stay the same. So the selection of the distance function is also very important. And then we go through a multiplicative updating iterative rules to keep iterating the estimation so that the value that we get for H and W would be close enough so that we can extract those three signal out, right? Now, and there's some discussion about is it converge? What's the local minimum, and what are the number of key components in the original signal? Those are the details that I have discussed in our paper published just last year in a conference called Census. So please refer to the paper for more detail, or just shoot me an email if you have any question. But what I just discussed is with an assumption that we know where to start, right? Because if we go through the iteration and we try to do the optimization, but we don't know what the value of W is, and if you start from a metric of 0, then it would take forever for us to converge. Or we can go into a local maximum. So what we do is that we applied a single class support vector machine to learn the basic pattern of the signal. And the key idea here is that if we can represent, we can seek for the hyperplane P that can separate the data from all the data point maximum from the origin, then we can estimate the metric W. So again, I would refer you to the paper for more detail. But the high level idea here is that, okay, so we would need to have a machine learning step to learn the core pattern of the signal. And then during the online process, we would try to extract the signal out by going through the iteration process. Okay. Now, that is the first challenge. And by proposing the new algorithm, by using that algorithm, we can split the signal out if we have relatively good signal that capture from inside the ear. But the challenge here is, the second challenge is coming from a practical and design challenge where, as I mentioned, we have a very small ear canal and even smaller with baby and kids. And during sleep, this ear canal can be easily deformed because if you turn your body, the pillow would press against your ear canal, it becomes smaller, right? And then if you have an earpiece that is hard inside the ear, then it will be very painful the day after if you wake up, right? And now if you have a piece that's really soft, then when you turn back from that pressing position, then the earpiece might not have a very good contact point with the inner, with inside of your ear, right? So that is challenging. And also at the same time, even though we're saying that it's pretty close to the signal source, we still need to have a very good contact point, the contact area between the earpiece and inside the ear. So what we came up with is just a practical solution, but actually work that we use a viscoelastic foam, and the nice property about this is that it will go back to its original form as soon as the force against it go away, right? So when you sleep, if you turn and there's a pressure, then the foam would shrink. But when the force is no longer there, it will expand back to the original shape. But this is not conductive, right? So we have to have a layer of electrodes that attach on the surface of that earpiece so that we can conduct the bioelectrical signal out. So we started out with silver, right? Silver has a great property that it's highly conductive, very low resistance that can conduct the signal out very well. The problem though is that in order to use this, we have to squeeze it every time you put into your ear. And then it will expand out. But if you try to use pure silver, you realize that as soon as you squeeze it, it breaks out. It's very, very easy to break, right? So what we have to use is that we would introduce another layer of material that we use conductive cloth. The nice property of a conductive cloth is, of course, it's very flexible, durable, and even when you squeeze it, it will not break, right? And then we glue using medical glue and conductive gel that stick the silver layer on top of those cloth. And by doing that, now we have a earpiece that is conductive, flexible, comfortable, and also it's very, very low cost, right? Now, also we need to have a electrically shielded cable to take the signal out from that earpiece. So now with that, we were able to capture the signal and then apply the signal separation algorithms to split the signal out. And we were going back to the original question that we had, right? Can we use this system to capture sleep stage? So we derived we have a set of signal processings and machine learning steps to classify sleep stages of a person through a whole night's sleep. So we have a data processing step, and then signal separation, and then going through the sleep stage classification, which is very basic sleep stage classification algorithm. And then we tested this on 8 different patients for a duration of 38 hours. And what we've shown here is we compare our system. This is the earpiece that the subject is wearing, and then it goes into an open BCI board. And then we compare that with a gold standard polysomnogram. And this device was donated to us, but it costs around $50,000. Right, $50,000 is really expensive, and of course that is used as a ground truth device. And the question we want to ask there is, okay, after we split the signal and apply the sleep stage classification, how well can we do compared to the polysomnogram, compared to the gold standard, right? And what we see is that our algorithm can match up to 95% of accuracy compared to the gold standard device that costs about 1,000 times more. And this is something that we can do also at home, and it's much more comfortable, right? So, we further perform a number of experiments to confirm that we actually can capture the eye signal, brain signal, and muscle signal. I'll just go through a few of them here. So these figures show an experiment where we would have our subject wear an earpiece, and then we would the subject would sit down, and we ask them to look to the left, look to the right, look up and down. And we want to see if our device can capture that, right? The figure on top is the ground truth, which is the polysomnogram that has, we would use the electrode here to attach on different position on the face. And then we want to capture the signal. And this is the signal that we can capture using our device. And you can see that it's very clear that yes, there are significant peak of the signal that we can capture, right? It means that we can capture your eyes movement very well. One important point here is that even the ground truth device cannot capture up and down movement. The reason is that our ear is polarized. Our eye is polarized, right? The back is negative, the front is positive. Now, as you move the eyes, if you move horizontally, because the electrode is on 2 sides of your ear, right? If you move horizontally, we can capture the movement very well. Now, if you move like this, then the potential doesn't, the bioelectrical potential difference that it makes is very minimum with respect to the reference point from to ear. That's why we cannot capture it very well, and the ground truth cannot capture it very well neither, right? So, but the key point here is that we can capture your vertical eyes movement very well. Now, we can also capture the muscle signal very, very well as well, because the muscle signal is normally in order of millivolt or 100 of microvolts. So because of that, we can, in this experiment, we have the subject to chew and grind their teeth. And then we want to see if we can capture using our system. And you can see here, it's very clear that such event can be captured using our device. And we further validate our system to see if we can capture brain signal very well, right? So in this experiment, we perform a test called audio steady state response, where we would play sounds at 40 hertz, and we want to see if that stimulate any that it can stimulate the brain of the person, because if it does, then the system should, then on the brain signal, we should see a peak at the 40 hertz. And this is what we see, right? It's very clear that we can capture those peaks as well. And the same experiment is done with the visual sensory, where we have a steady state visually evoked potential experiment, where we have a patient look at a video that flicking at 10 hertz, and that we can see on the brain signal as well. And another last experiment we tried was that we have a person to sit down and just close their eye and try to drift into sleep. And what we want to capture is some delta wave, which is around less than 4 hertz. And what we want to see is, we want to capture is, okay, can we see that on our from the in-ear channel? And what we see is, this is a ground truth, which is the PSG. We can see that the signal amplitude is much larger, and it's also much clearer. But in our system, we also can capture that, right? So this is just to show that yes, we indeed can not only capture the eye signal and the muscle signal, which normally have a larger amplitude, but we can also capture the brain signal. And what we show so far is that yes, the system has an ability to capture and to perform sleep stage classification. But what else can we do with this system, right? So the first project that we have extended this sleep project to is a sensory overloading onset prediction for autism kids. So the problem with autism kids that have sensory overloading problem is that when they go into the environment where their sensors, including eye, visual, or audio system, have get overloaded, they would have start acting out, right? And when that autism acting out happen, it's very hard to calm them down. But using our system, we should be able to capture when the sensory system become overloading, because based on their brain signal, based on their eye signal, and based on their muscle signal, we can measure or estimate the level of stress that they're going through as more sensory information coming into their system, right? So with that, we should be able to predict the autism onset. And if we can predict it, we can prevent it, and then we can treat it easier, right? The second system that we think this could be useful is to help with meditation. It could be a meditation assistant or training system, because with this system we can not only capture your brain, which is there's another system existing system out there called Muse that can capture your brain signal, and from that it can tell you how well you are meditating, and from that they can advise or train the subject on how to improve their meditation, right? But with our system, we not only can look at their brain, but also look at their eyes and also their muscle to see the level of relaxation that they have, and hopefully can improve their meditation performance. Another system, another problem that we can potentially help with is a classical problem in hearing aid. And this is something that was brought to us by one of the audiologists in the hospital where we are working, where it's called a cocktail party problem, where the problem is that when you go into a cocktail party, the hearing aid device, the state-of-the-art hearing aid device now, would try to amplify the sounds coming from the area that has the loudest amplitude, that it sounds like a human's voice, right? So if you go into a party and if there's a group of people behind you are talking very loud, but you want to talk to the person right in front of you, the system will fail to support you with that, right? Because it would try to amplify the sounds that right behind you. But using our our technology, that we think that we can capture the area of attention, because based on your eye signal, we know whether you are looking backward or you are interested in talking to a person on the left, on your right, so that, and also we can combine the signal from the brain to see if you are pleased with the output that your hearing aid is producing, right? So with that, we can change or maybe steal the amplifications mechanism in the hearing aid, so that it will steal toward and amplify the signal and the sound of interest to the user, right? Another another application of this could be used for distraction and drowsiness detection. So this is a video that we found on Kickstarter where they have a headband device that try to detect your drowsiness. Would you wear that device? Probably not, right? Because it's not very convenient to wear something like that, and in fact the Kickstarter actually failed because of a various reason. Maybe it's because of inconvenience and also odd looking, right? But we think that using our technology, we can help with this problem because, for one, distraction can cause the indication of distraction can be from your brain signal, but also from your eye signal, right? If you're not looking straight, if you're looking down on your phone, then we probably can do some inference from the signal processing, and we can see that, oh, you're not looking forward, why don't you look back? And if you see the design of the system, right, it's really just two electrodes that attach on an earpiece. Now think about we integrate that technology into today's earphone, where we just attach two pieces of electrodes on that and then put all the circuit that you need to do signal processing and signal acquisition into maybe the volume control for the current earphone. Then we can augment today's earphone to sense those signals, right? And imagine that if the driver is listening to music wearing a earphone, and we can capture their brain, their eyes, and their muscle, we can tell whether they're distracted or not. We can tell whether they're sleepy or not, so that we can send the alert message to them. And another application that we can enable is eating habit monitoring, right? Where the motivation for this is coming from the fact that, well, if you're listening to music and you're eating and doing some other activities, and because we can capture your muscle signal very well, and by very well I meant it's compared to the other two signals, we can capture the muscle signal much better compared to brain and eyes, because the amplitude of the signal is about 1,000 times stronger compared to the signal coming from the brain or from the ear. And because of that, now we can infer how often are you eating? How often are you chewing? How hard are you chewing? Because based on the amplitude of the muscle signal, how much do you need to chew every time? So that hopefully from that we can infer the type of food that you were eating, the frequency of your eating, of course, but how much calorie are you intaking with some help from users, right? So with that, we can have a system that help people to regulate or recommend what they should eat, when they should eat, how much they should eat, etc. And this is by far my most the application that I interested the most, which is we should be able to estimate or gauge the children's interest, right? We all know that kids are from the age from 0 to 2, they don't have ability to express their interest. They would do what you give them to do, and the only way that to express their interest is crying. But most of the time, if you let them play, they wouldn't cry, right? But so this is a footage of a system that was proposed to gauge the interest of a kid. Of course, it's not that comfortable, right? But by augmenting the earpiece, by reading the signal from looks fun. So by looking at the signal that we can capture from inside the kid's ear, and at the same time we let them play different sport, and learn different subject, we should be able to infer what is the level of interest that they have for each of those subjects. And from that, we would orient them accordingly so that they can learn what they like the most, right? And last but not least is the ability to use this for human-computer interactions. Instead of doing brain-computer interaction, we should be able to do brain, eyes, muscle, computer interaction. Because if you combine those different signals, you would have, I expect that we would have a more reliable way of giving input to a computer system, right? Because the brain signal sometimes, it's even hard for us to fully understand, let alone control it. So if we can combine the brain signal with the eye signal and the muscle signal, then probably controlling the wheelchair should be more explicit, right? Not only accurate, but also more explicit. So what I was describing is different potential for this system to be applicable to, right? We can use it for different health applications or some of the applications that are less trivial. But of course, the only thing that we have tested is in-home sleep monitoring, where we have in-lab and in-hospital testing, but we haven't tried the rest yet. So what we're trying to do as a next step is we really tried to refine our prototype, to improve the signal quality, to pack it into a package where we can really send to our collaborator to try it out. And the goal is we try to we try to commercialize this so that we can enable the sleep classification algorithm, but also we soon will open source this for the research community to build on top of this. So if you are interested in either helping us with improving what we have now, or interested in using our technology, please come and talk to me, and I would love to provide either insight or even hardware that we have, or if you have any comments, I would love to hear from you. So I guess with that, I would stop and take questions, and I hope that I keep you all awake. Thank you. Yes.
So as I understand it, you have this mixed signal that you are picking up in the ear,
right,
that combines these various inputs, if you will, from the
right,
eye, the muscles, and the brainwave. Instead of trying to separate out the signals, have you tried just training the combined signal to
right,
see how well that does against your gold standard?
Right. So we've done that. We've done that, and the accuracy is about 3 to 4% less compared to the splitted signal. Now, if the goal is only to do sleep stage classification, then that is sufficient. But what we would actually want to enable is a wider class of applications. As I mentioned, if you want to capture eye signal and muscle signal to do autism detection or to do meditation.
You might want to separate them out, but I would
Right,
expect the error rate actually to be higher, because none of, if you do a determination of the separation, in order to look at the combination, because you'll have error in any of the separations that you're
right,
going to do.
Right.
Whereas if you have the ensemble,
right.
you won't.
So that is actually, that's the intuition that we had before we split. But I think the reason for us to get the higher accuracy is because of even if there are inaccuracy, the splitting algorithm was consistently having that same margin of inaccuracy, if you will. So that's why we still see the improvement in performance. But I agree with you that would be an intuition that's what we had at the beginning.
Yeah, especially with an SBM approach, I would expect that you would actually do better, because many of these things are correlated anyway with the different stages of sleep, for example.
I see. I think the question comes from there first. Please.
Me?
Yes.
Oh, thank you for the talk. I have several questions. First, I think you are using PSG device to provide the ground truth, right? And usually, like for medical experiment, you need like a physician to manually label the data.
Right.
So are you collaborating with hospital to get it?
We do. So we have our collaboration is with a sleep lab in University of Colorado and Colorado Children's Hospital. So the experiment was that we set the patient down, have nurse come in to set those up, and after we get the data, we get the result out of the PSG, the doctor would need to sit down and read through that, and we use that as a ground truth to compare.
How many doctors do you have?
We have one.
Only one.
Right. Yeah.
Because I think the standard in sleep studies is you need to at least have two, so that you can report the agreement read between multiple doctors. Then our experience is that like usually the human agreement rate between doctors on the PSG data is only 70 to 80%, but you can achieve like 95% accuracy. Usually like in PSG comparison results, anything higher than 85% is considered as meaningless because it's even higher than the ground truth agreement rate between multiple doctors.
So, as far as I know, in the hospital the hospital that we're collaborating with, we have 6 beds there, but only 1 doctor that are reading the result. And it is, so we perform 3,000 sleep study every year, and that's what it does.
It'd be much better if you can have like
have
at
more,
least
yes.
2 doctors to
Right.
look at the same data and to see how consistent the result will be combining these 2 doctors' reading results.
Right.
And another question is, I think you are using machine learning as part of your algorithm, right? So do you need training data from each of your subjects, or your model can be generalized to a subject it has never seen before?
So the signal separation algorithm required per person training. The sleep stage classification doesn't require per person training. So we can use the same patterns because it's the characteristic of the signal to classify what sleep stage you are at is relatively consistent.
I see, but I think the signal separation is also important, right?
Right.
That means like every time you have a new subject, you need to like have some his ground truth or measure his PSG for a while, then train your algorithm on the maybe very short ground truth, and then you can apply your system to the new subject.
That is a great point, and the answer is yes and no. So yes, if you want to, at the current state, that's what we need to do. We need to do per person training, but the reason for us to do per person training is because, well, the output of a per person training is a metric W, right? The metric W, which is because we wanted to factorize them. Now, if the metric W is not if you do per person training, you would have a very good metric for that person alone. But if the training set is large enough from which you can extract the W metric for all of them, right? Then the starting point for that might not be as close to per person, but after you go through a multiple iteration, you still can get a good factorization metric. And after you factorize them, that would still be accurate.
Yeah, so it'd be interesting to see the results, like if it can be generalized to new structure you have never seen.
Right. So we are actually working on that, but as I said, that's a very good point. That's one of the concern that we have. That well, if we want to do this at home, but we have to ask them to come to the hospital to get access to PSG. That's not practical. That's why we're actually collaborating with IBM on that to develop the algorithm to test on a larger data set. Because if we get a larger data set, we should be able to get a better W metric, if you will, so that we know that it's a general point that we can start for everyone, so that we can eliminate the need of per person training. But that's a great question. Thanks.
Last question. I think right now
We have a lot of time for questions.
in-ear interface, especially like in-ear EEG, is very popular. We have seen like several other devices developed by labs, maybe still not on market. And I think one of the main problems they are facing is it's perfect for like sleep monitoring, but very hard for like be used in the day because it has huge problem when people have facial expressions and when people are talking. Where every time you move your jaw, it will cause huge emotion artifact in any ear signal. So when you are trying to do it not for sleep but in the day, how would you like to solve the problem?
So I think that would be an inherent problem. And so far, what we do is that we try to have a bias electrode so that we can eliminate the. So what we measure is the voltage difference between 2 ears. It meant that if there's some movement happen, let's say from the lower body part, then that can be eliminated because we have the bias point that would cut those down. But yes, if you have a lot of facial expression when you talk, right? Then that would be that might be a concern. We don't have a good solution for that yet. That's why we started out with a sleep problem where we assume that you lay down and your muscle movement and muscle signal does not dominate the whole channel. Now, as a next step, what we have done is we have a new, so as I said, so this is the original board that we have, which is using OpenBCI. And the problem with that is what you mentioned, it would have artifact from other signal as well. What we have this is a new design that we have, and it's a custom board that we built that we split the signal from the analog channel. So because if we have a single channel, and then if the muscle signal happens, it can saturate the signal. Because again, brain signal is about 1,000 times weaker than the muscle signal, right? So what we need to avoid is the saturations of on one channel that prevent us from accessing to the other channels. That's why we have a dedicated hardware design to solve that problem, but we haven't finished it yet. It worked pretty well, but we will have more to talk about when we release the paper.
Looking forward to it.
Thanks. Great point. Yeah. I don't know who's next. I think, yes, please.
Okay. So if I understand it, so you're using the SVM to initialize your W matrix for the NMF,
yes.
Right?
Yeah.
And so the training data that you're using for that SVM, to generate the initialization, could you, if you wanted to, use that same training data to do kind of like a machine learned end-to-end system? Or is the data, I'm not super clear on what type of training data you're using for the initial SVM,
okay.
And then also how you would get the kind of source separated data that you would use to train a fully end-to-end system.
So what we have now is only 9 minutes of collecting data for signal separation, meaning that's not the end-to-end data that you need for sleep stage classification, right? Because for sleep stage classification, you need at least 1 cycle of sleep, which is around 45 minutes. What we did was we do 2 cycles of sleep, which is around 90 minutes, right? So for the training to split the signal, what we need is only the signal, a short chunk of signal, so that we know the characteristic of the signal. It should be long enough so that we can eliminate some of the artifacts because of you put the device in, it's still expanding, collapsing. That's why, and what we saw is about 9 minutes of training is enough. Does that answer the question?
So because to train the source separation,
right.
What you'd want to have is the mixture, and then you'd want your clean individual
right.
sources.
Right.
So how do you get those clean individual sources to train that?
We need to get that from PSG, because what the input for that training would be brain, eyes, muscle. And then we put the mixed signal in, and then we try to split them out.
Okay. And the clean signal from the PSG is similar enough to the signal that you're getting from your device.
Yes.
That
Good point.
you can use to train.
So the signal we get for training from the brain are from T3 and T4, which is relatively close to the inside the ear location, right? So that's why that's another reason for us to attack sleep problem, because the T3 and T4 are locations where the sleep doctors are using for their PSG. Thanks.
Super interesting. I'm really curious. I'm designing a study for PTSD patients that's focused very heavily on EEG. But I have a question. Have you modeled how interference from Wi-Fi or atmospheric noise affects your sensor?
We don't see a lot of interference from that. Well, let me put it that way. So at the beginning we saw that, but then when you have very well sealed cable, I think that would address a lot of the problem, because what the radio signal is, it introduced the electromagnetic interference, right? And that would only affect your system if the wire are creating a loop, like an antenna. Now, if you have a very straight line, straight wire, or you have well sealed wire, you should be fine. We do though see, I think the main source of noise are coming from the movement of the different part on your head.
Am I good?
Yeah.
So you're just mentioning that you're using T3 and T4.
Right.
Aren't those normally referenced to the top of your head?
So that is what so the sleep doctor are currently using T3 and T4 and I think C3 and C4 are on top of their head, right? T3 and T4 are here.
No, CZ. Like, since the reference is here and you're
Right.
using your reference from here
I'm
to
using
here.
the reference. So I'm using the channel so the channels are T3 and T4 in the normal 16 electrodes EEG system.
So it is a typical system?
Yes, it is
Okay.
typical system.
Did you ever check the correlation between what you were getting and what it was spitting out?
Yes. So that was I have a few figure that I shown there, right, where we can see, can we see the signal when you drift into delta, for example? So that's where we capture. That's where we get the ground truth, and we compare with our in-ear.
Okay.
Right.
Interesting. And then the other thing I was curious about, up there, it looks like you're using multi-channel. Are you
So-
expanding electrode count?
Well, this is a debugging board that we have, because as you see that we have a number of probes here, and you're right, we have 8 channels on this circuit because we want to see, okay, what's amplification factors that we should use. So this is in development. That's why we're saying that when we finish, it should be smaller, 3 channels, and with different amplification, with adaptive amplification.
So you're going to go up to 3 channels?
So we only get 1 channel in. We split out 3 channels, and those channels would have different analog signal processing to get the signal what we want, which is brain, eyes, muscle, and then go into the DSP, which have the algorithm that I just mentioned. Yes.
Have you guys checked how much the variance of where? So the design you have has it go pretty deep, like 1,000 per second band, and
Right.
I'm sure you guys weren't getting that in even the eight male female participants you guys had. And so how much did that impact your guys' ability to get a clean signal to sleep states? Like, is that 95% average across these 8, or that you had much better in some? Just yeah.
So in the study that we have done, the electrode was pushed in at the beginning of the study by the nurse. Right, so we make sure that the contact point was good, the signal was clean. But I agree that would affect our system as well. But by design, as I mentioned, the distance metric that we have is there to take care of the variance when you have the contact point variations in quality.
So have you guys done anything where, like, for example, you put the electrode
All the way out?
like in your concha, not all the way in your
We haven't done that,
Not-
but I think that should be something that is something that should be evaluated.
Okay.
Yeah.
One other question is with regard to the 5% error that you, or the 95% accuracy relative to your PSG that you're doing,
Mhm.
was that largely attributed to, like, for example, only having 2 of your EEG locations as opposed to the 16 that they use in normal PSG? Or like, was that due to your machine learning algorithm? Have you guys kind of attributed where most of that error is coming from?
We haven't looked at that. We haven't tried to localize what the source of the problem was. I think it's mainly because of the inaccuracy of the when you learn with a small set of data, and then I think the training data set is too small. If we have a larger data set, we probably can improve it. Yeah, right. Please.
Thanks for the talk. I was wondering if you talk a little bit more about something you mentioned in passing, which was the auditory attention work that's kind of coming up, and to what extent you're kind of doing sensor fusion with other kinds of devices on the head or on the body. And I mean, as you're working with earplugs, like things that come to mind are things like glasses and electrodes on the nose, and
Right.
kind of other things that would add some context.
I think if we can add more sensors, and yes, we are working on many other sensors as well, we should be able to improve the accuracy of those applications. And it's always the question of where do you balance between the form factor, the social acceptance of the form factor, and the accuracy, right? For example, one of the main reasons for Google Glass to fail is because people don't want to wear that in public. So yes, we are exploring that, but we don't have data to share yet.
And kind of a follow-up on that, some of the applications you described are kind of unconscious sensing, like when you're sensing someone while they're sleeping. Others, like attention,
Right.
involve some kind of conscious, maybe sometimes implicit, sometimes unconscious
Right.
engagement with the user. To what extent do you think biofeedback, particularly with the sensor fusion plus these other kinds of sensing that you're developing, can be harnessed to kind of learn some kind of alternative to attention in a classical sense, but to achieve the same kinds of results? So as a hearing aid, someone with a hearing aid might be able to tune in through some training process to different things.
Right.
So you like are you interested in those kinds of questions, or are you looking much more at the classical notions of unconscious attention?
That is a very interesting aspect that we haven't thought about, but I think when we talk tomorrow, I would love to hear more about it. Yes.
What are some of the main differences you see in the in-ear sensing system than traditional EEG stuff?
So I think the key difference is that when we measure from in-ear, we don't have the resolution that you would normally have with 16 electrode, 30 electrode, or 60, or even 128 electrodes, the traditional EEG systems, right? So what we get is really the aggregation of those signals that result in the two measurement point. I think that is a trade-off that we consciously make between the comfortness, the cost, and also with respect to the resolution and the accuracy. Because I think the traditional way is still much more accurate, right? Because you have a closer contact, the closer distance between the measurement point to the signal source, right? So I think, again, that's a trade-off.
Do you know where more of the noise might be coming from? Could it be from generated inside the ear, or?
So do you mean the electrical noise, right? So I think if you want what we found is measuring the brain signal is the most challenging part, right? And it's mainly because of the amplitude of the signal. It's really, really small. It's small, and it's a combination of many other signals. So that's why it's challenging, and the noise we see that is mainly from when the eyes move. It's not actually just the eye signal. It's a muscle that controls the eyes and the eyes itself. So it's a complex, revolving of a problem that we found that it's challenging to split them when it all happened at the same time, right? Yes.
Me?
Yes.
Sorry. I had a couple of quick questions. Thank you for
Yes.
for the talk. It's a really exciting field, and I appreciate you coming down here to give us some insight.
Thanks.
One of the things that you mentioned that you're checking T3 and T4.
Right.
So sleep spindles for stage 2 and stuff are mostly like fronto-central. Are you picking up like sleep spindles, K complexes, things like that to be able to stage 2 accurately?
Right.
And then the second question going on to that is that under 95% accuracy, were there certain sleep stages that were more accurate than others? Like you were easily able to pick up deep sleep compared to stage 2, for example?
Right. So first question, yes, we can capture spindle and K complex very well. And the doctor can actually look at the signal and say, this is spindle, this is K complex. And she was very excited about that. Now, the second question is, what are the confusion that we normally have? So REM is the easiest one to capture. So what we normally confuse is between state number 2 and state number 3. So I guess that's mainly because I think of the training that we have, because we don't have a lot of data on that too, neither, right? When we have built our machine learning model. Yeah.
And I noticed in your average age is 25. So I wonder, I think when you're younger, like you tend to see signals everywhere.
Right.
As you get kind of older, like you might not be able to pick up the differentiation of the sleep stages as well. Have you checked like a little bit older groups or?
So that is like, we have an IRB for that, and we are recruiting more older, higher age populations. And not only that, I think it would affect by because the age would affect not because of the signal itself, but it's also affected by the sleep habit, I think. What we have here is a group of the subject mostly are graduate student and undergraduate student. Now, if the average is 35% of the American population having sleep deprivation, I think that ratio is probably 60 or 70% of undergraduate and graduate students have sleep deprivation, right? So what that meant is that if you put them down to sleep, they sleep immediately and they go to the deep sleep stage very, very quickly. So that account into the result as well, right? But it definitely affected by the population that we picked. Yeah.
Did you also run into any picking up the auditory nerve, which is in the ear? Did you have any trouble with the noise from that?
So I did not get the question. So will that cause any noise?
So there's the auditory nerve that kind of runs in the ear.
Uh-huh.
So I'm wondering if your EEG signal or like the noise that you're getting in your signal, were you able to tease that apart from
I see.
like is the auditory nerve causing a problem?
I see. We don't. We don't see that.
You don't see it, okay.
But we, I think because we don't know about that. I would love to hear more about it, and we would explore that to see if that's the case. Right. Yeah.
And then I guess my last question is going back to, you mentioned the noise, like one of the challenges was the brain signal is so small, it's hard
Right.
to get that.
Right.
What are some other big, and you've tackled a lot of challenges, but what are some of the big challenges that you've had in terms of getting the algorithm down and things like that? What was the trickiest parts that were tough to master?
So I think the one of the factors that prevent this from being practical, oh well, it is practical, but we can make it more practical by eliminating the need of having a single per-person training. That's one of the key challenges that we need to address, because as one of the questions was raised, right? If you have to do training and you have to take them to the hospital, it's defeat the whole purpose of doing in-home study. I think that if we can address that, that would be a big advantage. Now, the second problem is the material that we are using. So currently we are using viscoelastic foam and silver, but what we are looking at, and we have a few companies that are helping with is we try to have the material that we can mold the earpiece into a single piece, so that it's more durable, more reliable, and it's easier to use instead of squeezing it in. So this is the device that we were looking at, and this is something that we aim for, where we really mold those earpiece as opposed to have manual process of making it. Yeah, that would help a lot too. Yeah.
Okay. Well, thank you,
Right.
everyone, for coming out. And do we have your email address in case anyone else
Right.
has more questions? And Tam is still here, but he's kind of scheduled for the
Right.
rest of his time. But you can always send him email. So thank you.